Hello, I Anand Jain from Hanumangarh, Rajasthan welcomes you to your favorite Shridevi classes YouTube channel where we inculcate interest and confidence in physics subjects. Today we will remove your doubts and confusion in one physics topic which is a probable question pattern for our board examination 2, and we'll discuss magnetic force between two long straight and parallel current carrying conductors, and we'll also define international standard definition of 1 ampere. So let's understand ampere magnetic force concept and increase your marks in board examination. Magnetic force of attraction when current is in the same direction, or force of repulsion when current are in opposite direction between two long straight and parallel current carrying conductor or wire separated by a small distance is often called as ampere force law. Physical origin of this magnetic force is that every current carrying conductor generate magnetic field surrounding it, and interaction of magnetic field produced by two currents generate magnetic force here. The direction of magnetic force by a straight conductor is given by Maxwell right hand thumb rule, and thumb of right hand when aligned with this black I1 current in upward direction will find that surrounding this conductor in anti-clockwise circles there exist magnetic field B1 shown by black circles. Similarly, current I2 in this second conductor also generate anti-clockwise circled magnetic field around it. As per Biot-Savart law, magnetic field produced by a small elemental current length at r distance from it is given by this relation, and total magnetic effect of entire long straight current carrying conductor can be obtained by integration. And when a second current carrying conductor I2 having L length is placed in the magnetic field produced by first current, then as per Lorentz force formula it would have magnetic force. So current carrying conductor in magnetic field experience force, and that become source of force among two straight long parallel current carrying conductor. Consider two long parallel straight current carrying conductor at a small separation d carrying current in the same upward direction as shown here, and as per Maxwell right hand thumb rule, the both will produce magnetic field around them in the form of concentric circle given by the curl of right hand fingers when thumb is pointing in the direction of current, and both current produce anti-clockwise circled magnetic field as shown by for I1 current in black circles, and for I2 current it is in brown circles. And it is clear that one current in the magnetic field of second is placed such that the direction of current and direction of magnetic field are mutually perpendicular, as here magnetic field of I2 current is perpendicular to this screen outward towards us, and current is as shown by black line. So current and magnetic field at both conditions are mutually perpendicular. At the position of second parallel current I2, the magnetic field of first current B1 at a distance d from this long straight conductor is given by this relation. Magnetic field is mu 0 I upon 2 pi d, where I is current in conductor and d is perpendicular distance of observation position. And since this second current I2 normal to this screen towards us is placed in this magnetic field produced by first current, and the angle between the two is 90 degree. I2 current carrying length I2L in the magnetic field produced by first current B1 experience a force given by Lorentz force formula, and since angle between I2 current and B1 magnetic field is 90 degree, so this cross product is BIL sin 90, where magnetic field is produced by first straight long conductor at d distance from it is mu 0 I1 upon 2 pi d, and L length of I2 current will have this much amount of force, and the direction of force is normal to the plane of current length and magnetic field vector, and it is given by Fleming's left hand rule. And as per left hand rule, when middle finger is aligned along magnetic field which is inward here and central finger is towards the current direction, then the thumb of left hand will indicate the direction of force, and it clearly indicates that two parallel current carrying conductor carrying current in the same direction generate attractive inwards force as shown here. Similarly, this straight current carrying length having I2 current also produce its own magnetic field, and it is B2 at d's distance from it normal to the screen and given by this expression mu0 I2 upon 2 pi d, and in this B2 magnetic field perpendicular to it, I1 current is carried by this long straight conductor, and current carrying conductor in magnetic field again would have maximum amount of magnetic force as magnetic field and current are mutually perpendicular. At the position of this I1 current, the magnetic field of second parallel I2 current is B2, and at d distance from long straight conductor, magnetic field is mu0 I2 upon 2 pi d, and as per right hand thumb rule, the magnetic field around I2 current in anticlockwise circles got perpendicular to this screen towards us dot direction. So here current of straight conductor and magnetic field are mutually perpendicular, and current carrying conductor in magnetic field will have Lorentz force given as cross product of current element length vector and magnetic field vector, and it is BIL sine 90 degree as angle between current length and magnetic field is 90 degree. If we substitute magnitude of magnetic field produced by I2 current at d distance mu0 I2 upon 2 pi d, then this force is mu0 I1 I2 upon 2 pi d multiplied by length of conductor 1, and the direction is perpendicular to the plane of current length and magnetic field, and it can be obtained by either Maxwell right hand corkscrew rule or Fleming's left hand rule. And if we apply Fleming left hand rule, when thumb, forefinger and middle finger are stretched mutually perpendicular and forefinger indicate the direction of magnetic field of I2 current at this I1 conductor position, and central finger indicate the direction of current in I1 conductor, then the thumb indicate force on current carrying conductor in magnetic field, and it clearly indicate that when parallel current are in the same direction, the force is attractive towards each other. So force between two long straight parallel current carrying conductor carrying current I1 and I2 at d distance in air is mu0 I1 I2 L upon 2 pi d, and force per unit length, when we divide force by length get cancel out here, is given as mu0 I1 I2 upon 2 pi d, and this clearly indicates that force on first conductor by the current of second conductor and force on second conductor by current of first conductor per unit length is the same, and when the two currents are in the same direction, the force is attractive. We can remember that magnetic force between two parallel currents is just opposite to electrostatic force of stationary charges, where identical charge repel each other and here identical direction attracts each other. Now this attractive force per unit length will become basis for the definition of one unit of current. For example, if current in first and second conductor both is of 1 unit magnitude 1 ampere and the separation in air is again 1 meter, then in place of I1, I2 and D, when we substitute 1 each, we'll get that force per unit length on two parallel conductor will become mu naught upon 2 pi, and for air or vacuum the value of medium permeability is 4 pi into 10 to the power minus 7 Henry per meter, and when we divide it by 2 pi, the force per unit length comes as 2 into 10 to the power minus 7 Newton per meter when current in conductor is 1 unit and the separation is 1 meter in air. So force on second conductor by current in first parallel conductor is given by cross product of current element length and magnetic field vectors, and magnetic field of first current is mu0 I upon 2 pi d, and with 90 degree angle between magnetic field and current, the force of attraction for two similar directed parallel current is mu0 I1 I2 L upon 2 pi d, and force per unit length comes as mu0 I1 I2 upon 2 pi d, and if we substitute both current I1 and I2 1 unit and separation is taken as 1 meter, then force per unit length comes as 2 into 10 to the power minus 7 Newton per meter, and we can define 1 ampere is that constant current which, if maintained in two straight very long parallel conductor which are placed in air at a distance 1 meter apart, would generate a force of 2 into 10 to the power minus 7 Newton per unit length of those conductors. So if similar current in two parallel long conductor at 1 meter spacing generate 2 into 10 to the power minus 7 Newton force per unit length, then that similar current is 1 unit or international standard 1 ampere. By similar analysis, we can show that force is repulsive between two parallel current carrying conductor if current is in opposite direction. As per Maxwell right hand thumb rule, the magnetic field of this magenta I1 current is perpendicular to this screen plane and inward as thumb of right hand when aligned along current, then this curl of finger around this conductor in anti-clockwise circles indicate inward normal to plane direction of magnetic field by I1 current. Similarly, for Shan I2 current in downward direction, when thumb point the direction of current, the curl of finger indicate clockwise direction of magnetic field around this current, and that's again normal to this screen and inward as shown by crosshair. And when current carrying conductor is placed in magnetic field, it would have Lorentz force, and for 90-degree angle between current and magnetic field, force magnitude is maximum, and the direction of force is given by Fleming left hand rule, and which is repulsive as shown by thumb of this left hand. When the forefinger is directed along the direction of magnetic field and middle finger indicate the current, then thumb indicate the magnetic force on current carrying conductor placed in magnetic field, and for opposite directed current, the force is repulsive outward as shown here. Similarly, we can find out direction of force on second current by magnetic field of first current. The magnetic field is inward shown by forefinger, and the current in conductor is shown by middle finger of left hand. Then the thumb indicate the repulsive force. So when parallel current is in opposite direction, the force is of repulsive nature. The nature of magnetic force: attraction for identical direction of current and repulsion for opposite direction of current can also be explained by Michael Faraday imaginary concept of force lines. And if we see direction of magnetic force lines by these two cross inward current, then both magnetic fields are clockwise circles, and here opposite direction force lines cancel each other, so there is a decrease of force lines. And to oppose such decrement of force lines, the field interaction force the two currents to come closer, and there would be a force of attraction. Whereas when parallel conductor carry current in opposite direction, then for inward current it is clockwise circle, and for outward current it is anti-clockwise circle, and here force lines will get added up, and this increase in force line produce a field interaction such that force these conductor apart from each other, and there would be a repulsion force. So we can remember the magnetic force between two parallel current is opposite to electrostatic force of stationary charges, where identical charge repel each other, identical directed current attract each other, and opposite charge attract each other by electrostatic force, and opposite direction of current repel each other. We hope this learning video has solved one of your exam problem, and now you can score high marks when similar type of questions would be asked in your examination. Our other learning video of the similar Confused in Physics series are equally useful. You can use them in your study or share them to your friends. As you know, when you spread knowledge, you enhance your knowledge. Happy learning. Have a nice time. Thank you very much.